Hi, in this video, we're going to go over the practice exam problems. The first question, the z and v are defined. Z is defined as a plus bi, and v is defined as c plus di. And if you guys take a look, it has to do with these conjugates. So let me write down the definitions of conjugates first. So we know that since z is defined as this, it's going to be z, the conjugate, sorry, there's a bar above, that's going to be a minus bi, and the conjugate of v is going to be c minus di. So after you guys write this, let's start. I'm going to do A. So how you do the proving problems going forward, you want to start with one side and manipulate it until you get to the other side of the equation. So in this case, I'm going to start with the left-hand side, and that's going to be z plus z bar, which is the z conjugate. So I'm just going to substitute the definition of z, which is a plus bi, and the definition of the z conjugate is a minus bi. And those two things are being added right now. And when I do this, notice how there's a positive bi and a negative bi. They are going to be canceled, so I am left with 2a. And then I think I'm getting awfully close to where I'm supposed to end up. So this is the same thing as 2. And notice how the real part of equation z is a. The imaginary part of equation z is b. Likewise, the real part of equation v is c, and imaginary part of equation v is going to be d. Okay, so this is going to be the real part of z. All right, and then this is the right-hand side of our equation, and this suggests that I am done with the proof. All right, so let's do b. So we have this huge bar above z plus v, so let's figure out what z plus v is going to be. So z plus v is, I'll start with the left-hand side, which is z plus v bar. So this is going to be a plus bi plus c plus di, and this entire thing is above a bar. I'm going to group the real parts first, so I'm going to do a plus c, and I'm going to group the imaginary parts as well. So it's going to be b plus di, and there still is that conjugate portion. And what happens if we have a conjugate, then the sign in the middle switches, so we have a plus c minus b plus di. Okay, we have to somehow get this in the conjugate of z plus the conjugate of v. So let's expand this further. I'm going to distribute the negative into b plus d. At the same time, I'm also going to distribute the I. So this now becomes a plus c minus bi minus di. Okay, and I'm going to get these together. I'm just going to do some regrouping. So I'm going to write a minus bi first, and now these two together in the later part of the equation, c minus di. And I think I'm almost close, very close of finishing up. So I noticed that a minus bi, this is the conjugate of z, as we noticed, so this is the conjugate of z. And also c minus di, this part is the definition of the conjugate of v. So I can write conjugate of v, and this is identical to the right-hand side, and I am done with the proof. Okay, so let's go on to the next question. So this ends up what the solution is going to be. I'm sorry, I didn't realize that this would be kind of petty and it's too algebraic. So I'm going to delete the recorded portion of the video and just get rid of number 2. So again, I'll say this and I'll post the announcement that number 2 is not going to be on the test. Again, I think it's more of a skill that should be tested on the algebra class, not in differential equations. Okay, so now let's go on to problem number 3. This is another proving question that every polynomial of degree 3 with real coefficients has at least one real root. So there are different ways about doing this. You can prove that this is, if something has a degree of 3, then you can prove this by graphically that it's either the ends of the graphs looks like this or the other way. And it's going to be either this or this, right? So I'm just showing you guys the end behaviors. So what this means is, for example, if you have y equals to x cubed, then your graph would look like this, right? And if you have y equals to negative x cubed, then your graph would look like this. So if you have something that is going up and another side is going down by the nature of the degrees, then you know that it should cross the x-axis at least once. So an example of this is an example where the graph touches once. It may be the case another third degree equation may look like this, right? In this case, your graph is touching 3 times. In another case, you might have a graph that looks like this. In this case, you would have two solutions because it's going to touch the x 2 times. So this, by graphically, this was a quick proof that every polynomial of degree with a real coefficient has at least one root. So this is the case; it has only one root. Likewise, this is the case another with one root. This is the case where it has 2 roots and 3 roots. Okay, and you can take other. You guys can take the traditional algebra method if you have taken real analysis or abstract algebra in terms of proving this, but graphical proofs are fine with me. All right, let's go to the next question. So if theta x is given as this, where a is the real constant, then we have to show these differential equations exist. Okay, so apparently that is not supposed to be there. I'll go ahead and fix that. But if you are using the first version of the study guide, then you will see this, but just pretend that that's not there. Okay, so let's begin with the first one. It looks like we have to do a differential of the first time, so let's do that. We have the theta of x, that's going to be, this is e to the x formula. So we have, we're going to use the chain rule that I, a, x, we have to differentiate this, and e to the power of, that's going to be just copied. So what we have is I, a, e to the power of I, a, x. So this is what we have. Okay, so now let's plug this in to here. So I have I, a, e to the power of x minus I times a and just the theta of x. So we have e to the power of e, a, I, a, x, and it looks like they're exactly the same thing but subtracted, so this indeed is 0, and that's it. So A was pretty easy. Let's go on to B. Apparently it looks like you have to differentiate it twice, so let's do that. Okay, so this was our first differentiated answer, so let's differentiate it twice, which means that IA times, that one is also another chain rule, so the differentiation of this will come to the front and you get to the power of 2, and e to the power of IAX also gets kept. All right, so we can go ahead and IA is multiplied by itself two times. So this is the same thing as I squared, A squared, e to the power of IAX. And what's I squared? That's -1. So we have -1 I squared e to the power of IAX. Now we need to substitute this to here. So let's do that. We have negative a squared e to the power of IAX and plus a squared, and theta x is just that, so we'll substitute that again, IAX, and this again becomes 0.